All right, so you're here, which means you're ready to dive deep, but without drowning in information overload, right?
That's exactly what we're all about here.
We take these dense, complicated things like research papers and articles, and we break them down.
We extract those golden nuggets just for you.
It's the deep dive.
And today, we're diving headfirst into the world of neural networks.
Ooh, neural networks.
Specifically, we're going to explore how we're pushing them to adapt to brand new situations. And we're going to focus on these fascinating structures called graphs.
Okay, graphs. I'm intrigued already.
We have this really cool research paper as our roadmap. It lays out how researchers are making a big leap forward, getting graph neural networks, GNNs for short,
GNNs.
to go beyond their initial training. It's all about generalization.
Generalized beyond their initial training. That sounds like a big deal. What's the main hurdle there?
Imagine, right, you're teaching an AI to recognize cats, but you only show it pictures of tabby cats.
Tabby cats. Okay.
Then you show it a Siamese or a Persian.
Hmm.
What happens?
It probably freaks out.
It might really struggle, you know? It's never seen that kind of variety before.
It's like, wait, this is also a cat. My
I
world
think
is
it-
crumbling.
Exactly.
Right.
And that's essentially the challenge we're talking about here. Out of distribution generalization.
Out of distribution generalization, I'm writing that down. So why are graphs and these GNNs, why are they particularly tricky when it comes to this whole generalization thing?
Well, think about the sheer variety of graphs out there.
Yeah.
We have social networks,
Social networks.
road networks,
Sure.
even the way molecules are structured.
Oh, wow. Yeah.
They come in all shapes and sizes with completely different ways they're connected.
So many possibilities.
Exactly. And GNNs are these powerful tools for understanding and analyzing graphs.
Powerful tools. Okay.
They help us do things like, predict drug interactions or find the best delivery routes.
Useful stuff.
But here's the catch.
Uh-oh. There's a catch.
We often need these GNNs to work on graphs that are drastically different from the ones they were trained on.
Oh, so it's like training on those tabby cats again?
Yeah, kind of. Imagine you train a GNN on small, local social circles.
Like a group of friends?
Then you ask it to analyze something as massive and interconnected as Twitter.
Whoa, that's a huge jump.
Huge. It's like expecting a map of your neighborhood to help you navigate a whole continent.
Yeah, good luck with that. So the GNN might learn patterns that work great for those small training graphs, but totally fall apart when faced with something much bigger or with a different structure.
Exactly. The training data and the real-world problem become fundamentally different. Our usual assumptions about how well a machine learning model will perform just go out the window.
Out the window. So this research we're looking at, it tackles this problem head on, right?
Yes, they really go for it.
And they're using this really common graph problem as their example, finding the shortest path between 2 points.
The shortest path. You encounter that every day using GPS or even just how data travels online.
Right, shortest path. Makes sense. So what's the new approach they're taking to solve this problem with GNNs?
They call it neural algorithmic alignment.
Neural algorithmic alignment. Catchy.
The basic idea is to build neural networks that actually mirror the structure of classic algorithms.
Oh, interesting, like mimicking how traditional algorithms solve problems?
Exactly. They believe that by baking this fundamental algorithmic logic into the network, it'll become much better at adapting to new situations. Just like a well-designed algorithm, it should work reliably no matter the input.
So algorithmic alignment, that's a cool concept. Can you give me a specific example of one of these classic algorithms that they're using as a model?
Absolutely. The paper focuses on this technique called dynamic programming.
Dynamic programming. Okay, I vaguely remember that from my computer science days.
It's like solving a big puzzle. You break it down into smaller overlapping pieces.
Smaller pieces.
And once you've got those smaller pieces figured out, you put them together to solve the big one.
Ah, divide and conquer.
Exactly. And finding the shortest path is a great example of this. Let's say the shortest way from city A to city C goes through city B.
A to B to C.
That means that path is made up of the shortest way from A to B and the shortest way from B to C. Two smaller shortest path problems.
Right, so the bigger problem contains smaller versions of itself. How do they translate this dynamic programming idea into the language of GNNs?
Well, there's this classic dynamic programming algorithm for finding shortest paths called the Bellman-Ford algorithm.
Bellman-Ford algorithm, got it.
And that's a key inspiration here. The Bellman-Ford algorithm, it works step by step.
Step by step.
In each step, it refines its estimates of the shortest distances between all the points in the graph.
So it's constantly updating its guesses.
It's like, okay, if I go through this neighbor, is that a shorter route? And it keeps doing this until those shortest distance estimates settle down.
So it's an iterative process, a repeated cycle of updates.
Exactly. And that's where the connection to GNNs comes in.
Ah, the connection.
Message passing GNNs, they also work in layers.
Layers, okay.
And in each layer, every node in the graph updates its internal representation.
Internal representation, what's that?
It's like a little tag, a set of numbers that describe the node's properties. We call it an embedding.
Embedding, okay.
These embeddings get updated based on the embeddings of their neighbors and the characteristics of the connections between them.
So it's like gossiping with your neighbors and adjusting your own story based on what you hear.
It's a layer-by-layer process of information refinement.
Information refinement.
And that's very similar in spirit to those iterative updates in Bellman-Ford.
Ah, so both are refining information step by step. Now, this is where it gets really interesting for me.
Right, the big question.
How does mimicking this Bellman-Ford algorithm actually help these GNNs get better at finding shortest paths on completely new graphs that they've never seen before?
It's the heart of the matter, right?
Like, does it actually work?
And this paper doesn't just speculate, it provides really strong evidence.
Hmm.
Their main contribution is showing, through mathematical proofs and experiments, that GNNs specifically designed to align with the Bellman-Ford algorithm.
Okay, aligning with Bellman-Ford.
And trained with a focus on sparsity.
Sparsity, we'll get to that.
Can actually handle shortest path problems on graphs of any size or structure,
Any size or structure.
even if they've only been trained on small, simple examples.
Wow, that's a bold claim. Like, they can solve any shortest path problem.
It's a big deal.
What makes their proof so significant?
Well, think about it. In machine learning, you usually don't get those kinds of rock-solid guarantees.
It's more like, we hope it works well on new data.
This is different.
We'll come back to sparsity in a bit. But first, let's get a better handle on how these message-passing GNNs work at a basic level.
Right. Break it down.
So you've got your graph. Each point in the graph has this embedding, remember?
Like a little information tag.
Exactly. And these embeddings get updated over several rounds or layers.
Layers.
In each round, a point looks at the embeddings of its neighbors, combines that information, and then uses it to adjust its own embedding for the next round.
It's like sharing secrets and then updating your own based on what you learned.
Pretty much. There are two main steps involved. One, you combine the information from your neighbors.
Combine the gossip.
And two, you update your own embedding based on this combined information.
Ah, update your own story.
And of course, the characteristics of the connections between the points also play a role, like how strong the connection is or the distance between points.
Right. Those relationships matter.
Now, this research focuses on a specific type of GNN.
Right. They do. It's not just any GNN.
It's called the Min-Aggregation Graph Neural Network, or as we'll call it, the MinAG-GNN.
MinAG-GNN, okay.
In each layer of this MinAG-GNN, a node updates its embedding by doing something interesting.
Interesting how.
It looks at all its neighbors. For each neighbor, it uses a little neural network, a multi-layer perceptron or MLP,
MLP, got it.
to combine the neighbor's embedding with the weight of the connection between them.
So each neighbor gets its own little calculation.
Exactly.
Yeah.
Then comes the key part. It takes the minimum of all those results from its neighbor.
The minimum. Interesting.
That min operation is crucial because it directly reflects how the Bellman-Ford algorithm finds the shortest distance.
Ah, by always picking the shortest path available.
You got it. Finally, it uses another MLP to combine this minimum value with its own current embedding to get its new embedding for the next layer.
So it takes the shortest path, information from its neighbors, and incorporates it into its own understanding.
Exactly.
So the goal is to train this MinAG-GNN so that after a certain number of layers, its output is as close as possible to what you'd get from running the Bellman-Ford algorithm for the same number of steps, right?
Precisely. They use a symbol, OSUPSUP, to represent k iterations of the Bellman-Ford algorithm.
Sup. Okay.
The aim is to train the MinAG-GNN with all its adjustable parameters so that after L layers, where L is at least as big as k, its output matches what you'd get from running OSUPSUP.
It's like teaching the GNN to think like the Bellman-Ford algorithm.
Now, you mentioned a toy example. What was the purpose of that?
Ah, yes, the toy example. Why did they bother with that?
It's like a simplified illustration to help grasp the core idea. They start with this incredibly basic one-layer GNN. It only have 5 adjustable parameters.
5 parameters. That's tiny.
Super tiny. But they show that with the right values for those parameters, this little GNN can perfectly execute one single step of the Bellman-Ford algorithm.
Okay.
Then they imagine training this minimal model on a super small, specific set of graphs. They call this set small.
Small, okay.
This set only contains simple paths with 1 or 2 connections. No complicated stuff.
Really basic graphs.
And here's where it gets interesting. They have this key result, Theorem 2.2.
Theorem 2.2, the plot thickens.
It basically says that if the simple GNN achieves very low error on these tiny training examples in SHA-SMAL, then it must be approximately implementing that one Bellman-Ford step on any graph.
Hold on. Any graph,
Yeah.
not just the ones it was trained on.
Any graph. It's like saying if you can ace this kindergarten math test, you must understand basic arithmetic no matter what numbers you're given.
That's a pretty strong claim for such a basic setup and a limited data set. How do they prove that?
The proof relies on this thing called the ReLU activation function.
ReLU, I've heard it.
It's commonly used in neural networks.
Right.
ReLU acts like a switch. If the input is positive, it outputs the input. If it's negative, it outputs 0.
So it's either on or off.
This simple behavior limits the possible outputs of the GNN on those short path graphs. It means the output can only be one of a small number of very simple mathematical functions of the input weights.
Limited possibilities.
And because their little training set, very small, has enough variety to cover all these possible simple functions, if the GNN does well on those examples, it's forced to learn parameters that basically mimic the Bellman-Ford update rule.
So the training set acts like a guide, pushing the GNN towards the correct behavior.
Precisely.
Okay, that makes sense for the toy example. It's a glimpse into the underlying mechanism. But how do these ideas work with the full MNAG GNN, with its multiple layers and those more complex MLPs?
That's where the real breakthrough lies.
The main event.
For the full MNAG GNN, they use a more carefully crafted training set called GK.
GK.
This set includes longer path graphs and a slightly more complex graph structure they call H0K.
H0K. Okay, what's that?
It's visually represented in Figure 2 of their paper. Imagine 2 parallel paths, but with some extra connections between them, like crosslinks. They also include some very basic single and double connection paths in GK.
Okay, so a bit more complexity in the training set.
But here's the crucial part. When training the full MNAG GNN, they don't just use a standard error function. They use a special loss function called a regularized loss. They call it LREG.
Regularized loss. LREG.
Interesting. This LREG has 2 parts. The first part measures the usual error.
Yeah.
The difference between the GNN's predicted shortest path and the actual shortest paths.
Okay, standard error stuff.
The second part is where the magic happens. It's a sparsity regularization term. They write it as EAST20.
Eased. Okay, getting a bit technical here. What does that sparsity term do?
It penalizes the GNN for having too many non-zero parameters. Essentially, it encourages the network to find a solution that not only works well, but also does so using as few active components as possible.
So it's like saying, find the shortest path, but do it with the simplest possible set of instructions.
That's a great analogy. We're essentially pushing the GNN to learn the essence of shortest paths with the fewest possible ingredients.
Interesting approach.
And this leanness, this sparsity, seems to be key to its ability to adapt to new graphs.
So they're not just trying to minimize errors, they're also forcing the GNN to be more efficient by driving a lot of its parameters to 0.
Exactly. And this leads to their major theoretical result, Theorem 2.3.
Theorem 2.3, the climax.
This theorem basically states that if an L-layer MNAG GNN with those MLPs inside achieves a low value for this regularized loss on the training set GK, then the GNN's output will closely approximate running K steps of the Bellman-Ford algorithm on any graph.
Again, any graph. That's powerful.
Any graph. The error in this approximation is directly tied to how close the achieved loss is to the ideal lowest possible loss.
So the better the GNN does on the training set, the better it should generalize to any new graph.
That's the core idea.
That sounds like the central guarantee they're providing for real-world applications. How do they actually prove this more complex result?
The proof involves a few key steps. First, they show that a MNAG GNN can, in principle, implement K steps of the Bellman-Ford algorithm using a specific number of non-zero parameters.
So it has the capacity to learn the algorithm.
Then they argue that achieving low error on their carefully designed training set, GK, requires the GNN to have at least that many active parameters. This is because the specific structures within GK, like those simple path graphs and that H0K graph, force the GNN to use more complex internal functions and multiple layers.
So the training set is complex enough to ensure the GNN learns a good approximation of the algorithm.
Now, because they're also pushing for sparsity through that regularization term, the GNN is incentivized to find the most efficient solution with the minimum number of active parameters.
So it's finding the most compact way to represent the Bellman-Ford logic.
Right. And this sparsity constraint simplifies the GNN's internal workings to something that closely resembles the step-by-step logic of the Bellman-Ford algorithm.
It's like trimming away all the unnecessary complexity and revealing the core algorithmic structure.
Finally, they show that hitting that low error on the training set forces the remaining parameters to take on values that ensure the GNN accurately approximates the intermediate steps of the Bellman-Ford algorithm.
So it's not just learning the final output, it's learning the entire thought process of the algorithm.
Exactly.
So it seems like the sparsity regularization acts as a guide, steering the learning process, not just towards solutions that fit the training data, but towards solutions that embody the underlying structure of the Bellman-Ford algorithm.
That's a brilliant way to put it. Sparsity isn't just about efficiency. It's about aligning the GNN's internal workings with the algorithmic logic.
It makes you wonder how much of this is about the specific problem of shortest paths, and how much is about a broader principle of aligning neural networks with known algorithms.
That's a great question. We've talked a lot about theory, but what happened when they actually tested this out?
Right, the experiments. Did it actually work in practice?
In their experiments, they used a slightly more practical approach to encourage sparsity called L1 regularization.
L1 regularization. Okay. Why not stick with that in your thing?
Directly counting zero parameters, like an L0 regularization, can be tough to optimize in practice. L1 regularization achieves a similar effect, but is easier to work with.
Makes sense. Pragmatic choices. So they trained a two-layer MNAG GNN with L1 regularization and then tested it out.
Yes. They tested it using several different measures. First, they look at the error on the graphs it was trained on.
The training error, the usual baseline?
Then, they tested it on entirely new types of graphs it had never encountered during training, like cycles, fully connected graphs, and randomly generated graphs.
So really pushing it beyond its comfort zone.
Some of those new graphs were also much larger than the training examples. They also kept track of that combined error and sparsity measure to see if the regularization was working as intended.
Okay, so multiple ways to assess its performance. And what were the key findings? Did the models trained with this L1 sparsity promoting technique actually outperform those trained without it?
The results are pretty clear-cut. Figure 3 in their paper tells the story. The models trained with L1 regularization consistently had much lower values on that combined error and sparsity measure. More importantly, they had way lower error rates on those new unseen graph types compared to the models trained without regularization.
So the sparsity constraint really did help it generalize better.
They emphasized that the final error on those new graphs was dramatically lower for the L1 regularized model. This provides strong experimental support for their theoretical result, Theorem 2.3.
It's always good to see theory backed up by experiments.
Achieving low error while also keeping the model sparse leads to much better generalization to new kinds and sizes of graph problems.
So sparsity isn't just a theoretical curiosity. It has real practical benefits. What about the sparsity itself? Did the L1 regularization actually result in simpler, sparser models, as predicted?
Yes, it did. Figures 3C and 3TIC in the paper visually show this. The L1 regularization effectively pushes many of the GNN's parameters towards zero, resulting in networks with fewer active components. And crucially, these sparser networks seem to be approximating a sparse version of the Bellman-Ford algorithm, which lines up perfectly with their theoretical arguments.
So they're not just learning any old solution. They're learning a solution that mirrors the structure of the Bellman-Ford algorithm, but with fewer moving parts.
Now, they also tested the models on increasingly large, randomly generated, but sparsely connected graphs, as shown in Table 1.
Testing the limits.
What they found was that the L1 regularized model's error remained pretty stable even as the number of nodes in the graphs increased significantly.
So it scales well.
They even did another experiment. They took a model trained to perform just 2 steps of the shortest path calculation and used it repeatedly to solve problems that required many more steps.
Oh, clever. Like using a small building block to solve a much larger problem.
They found that with the L1 regularized model, the error didn't blow up over these repeated applications.
That's impressive.
But with the unregularized model, the error grew quite a bit. This shows a real practical advantage. A model trained on small graphs can be used iteratively to solve much bigger problems without losing too much accuracy.
So to sum it up, it seems like they've achieved something pretty remarkable. By designing the GNN architecture to reflect the Bellman-Ford algorithm, and by using sparsity regularization during training, they've shown that these networks can learn to solve shortest path problems on graphs far beyond what they were initially trained on.
That's right, even on graphs of practically unlimited size.
And they've backed it up with both rigorous mathematical proofs and solid experimental results.
It's a significant step
A
forward.
big leap.
It shows we can create neural networks that can reliably adapt to new, unseen problem scenarios, especially for tasks that have a clear algorithmic foundation.
It's not just about learning from data, it's about learning the underlying algorithm itself.
And the fact that you can iteratively apply the trained GNN to perform longer computations opens up a whole world of possibilities.
Right. It's like giving these networks the ability to think more deeply and solve more complex problems.
Absolutely. The model isn't limited to the number of calculation steps it was specifically trained for. It can, in theory, handle problems with arbitrarily long shortest paths.
That's powerful.
This also opens up exciting avenues for using these learned algorithmic building blocks in more complex neural network architectures. We could use them for tasks like optimizing delivery routes or making complex decisions based on graph data, where shortest path calculations are just one piece of the puzzle.
It really reinforces this idea of developing neural networks that can think algorithmically, that can reason like a programmer.
It's almost like teaching the neural network the underlying logic of the algorithm, instead of just having it memorize solutions for specific examples.
This could have broader implications for the field of neural networks in general. The researchers even highlight a connection to how transformer networks can sometimes handle longer sequences than they were trained on, possibly by learning similar iterative computational steps.
That connection to transformers is fascinating.
They suggest that these principles of algorithmic alignment, combined with sparsity, could be the key to achieving better generalization across a wider range of neural network architectures.
It raises some fundamental questions. When can we be confident that achieving good performance on a training set will translate to good performance on completely different problems for other types of neural networks?
Right. What are the special properties, the secret sauce, that enable such strong generalization guarantees?
Those are the big questions that this research pushes us to confront. It suggests a promising new direction for future research, maybe even a unified understanding of how to build truly reliable and adaptable neural networks.
It's a deep dive that's left me with a lot to ponder. We've explored some cutting-edge research and come away with some truly exciting insights.
It seems like by looking to the wisdom of those classic algorithms and by carefully shaping the learning process, we can empower neural networks to think more abstractly, more flexibly.
It's like giving them a shortcut to understanding complex domains.
And it challenges us to think differently about how we design and train AI systems, moving beyond just data-driven approaches and incorporating more of those foundational principles of computation.
So as you go about your day, think about where else these principles of aligning neural networks with known algorithms and encouraging efficiency through sparsity might apply.
Think about those areas where AI needs to go beyond what it's seen before. What does it mean for creating future AI systems that can genuinely reason and solve problems in new and unexpected situations?
It's definitely food for thought. Thanks for joining us on this deep dive. Until next time.
See you on the next deep dive.